Yeah, all right, everyone. I hope you can hear me. Can someone just confirm that?
Yes, sir, able to hear.
Yeah, and the screen is also visible, right?
Yes, sir.
Yeah, yeah. Good. So I guess we are doing this fluid mechanics, and we had covered fluid kinematics, and we are looking at some fluid statics problem right now. And this is one of the problems that I actually gave you as a homework. And so, anyone has tried this one? Anybody wants to tell me how you solve this? Anyone? Okay, no problem. We will see how to solve this. Let's read the question first. So a solid spherical bead of lead and some density is given, has some diameter, and it is sinking with a constant velocity v in a large stagnant pool of liquid, and the viscosity of this liquid is given to us. Now the coefficient of drag is given by CD is equal to 24 over RE, where RE is the Reynolds number. And we had seen in the last class that the definition of a Reynolds number, when it is defined on the basis of the diameter, is this. So this is rho times V times d over mu. And the drag force acting on the bead is expressed as T. So they have given some expression of what the drag force is. So just need to plug everything into this formula. That's the hint. And we need to calculate this velocity v with which this spherical bead is sinking. Okay, so let's first look at some of the concepts that we need to solve this. So we have discussed this Reynolds number defined on the basis of diameter is rho Vd over mu. Now this Reynolds number is very important non-dimensional number in fluid mechanics, which in general gives you the characteristic of the flow. So you can have laminar flow or turbulent flow, and you can characterize that based on the value of the Reynolds number. But here that is not necessary to us. We just need to know the expression of Reynolds number, and so this Reynolds number is just the ratio of inertia force to viscous force, and this viscous force comes because of the inertia force will come because of the body, and the viscous force comes because the fluid has some viscosity with which it opposes the flow. So it's like a frictional force. And so when you take the ratio of these two terms, you get an expression like this, where rho is the density, v is the velocity, d is the diameter, and mu is the coefficient of viscosity, or just the viscosity of the fluid. Also, let's look at the forces that the body experiences when it is sinking in a fluid. So here I've made this diagram where this black dot represents some kind of spherical ball which is sinking in this fluid. So okay, yeah, here I've written this is the fluid. When it
Sir,
is
can we go to the question for a second? Thank you.
uh, you want me to repeat the question?
No, sir, just show the question for a
Okay,
minute.
sure, sure.
Yes, sir, thank you, sir.
Okay, yeah. So as I was saying, let's say we have this fluid and some body here. Let's say this is a spherical body which is sinking in this fluid. So it will experience a bunch of forces. Let's look at all these forces one by one. First thing is, since this spherical ball has some weight, so it will experience some force due to its weight, which is called it's just the weight, and this is simply given by the mass of the ball times the gravity. So this is your conventional notion of uh, force because of the weight or the gravity of the body. This is acting downwards. Now, we had seen in the last class, whenever you immerse a body into a fluid, that fluid exerts a opposing force on the body called as the buoyant force, and that force is just simply the weight of the volume replaced by the body, the weight of the volume of the fluid that is replaced by this body. So this will act in the upward direction. This is called the buoyant force. And also because now this fluid has some viscosity, so this is not a inviscid fluid. So this has some viscosity, and the tendency of this viscosity is to oppose the motion. And since the motion is going on in the downward direction, you will have this drag force acting upwards uh, because of the viscosity of the fluid, and this drag force will try to retard the motion. Now, so we have these three forces coming into play, and if you have some acceleration in the body, then it will, so the acceleration will be given by the balance of these three forces, or the imbalance, you can call it. Okay, so yeah, knowing all this, let's try to solve this question now. So let's make the schematic. Let's say this is
Sir,
just
option C.
yeah, you're right, Ashwin. The correct option is C. So this is some fluid in which this spherical ball is immersed, and let's just note down what all is given to us. So you have the density of the lead bead or the spherical ball as 11 into 10 raised to the power 3 kg per meter cube. Now you have the diameter of the ball as 0.1 mm. So this will be zero point 0.1 into 10 raised to the power minus 3 meter. Better to always convert everything into SI units. Now the viscosity of the fluid is given. Let's represent that by mu, and that is 1.1 times 10 raised to the power minus 3 kg per meter second. They have given us the coefficient of drag as 24 over RE. Now this RE we need to calculate. We will do that. And okay, the velocity with which the bead is going down is, so this is a constant velocity first of all, and this velocity is V. So this body is, okay, let me take another color. Yeah, so this body is going down with constant velocity V. So this means that it is not experiencing any external force because this is a constant velocity, so it is not accelerating. Now let's try to, okay, one more thing we need to note is that they have asked us to neglect the buoyancy force. So that FB in the last slide, so this FB won't be here in this question. We will just have the weight of the ball, which is given by m times g. So this is W, weight of the ball given by m times g, and you will have some kind of drag force because this fluid is viscous, and that drag force is given by this expression T. Right. So if that is the case, then it's just a matter of balancing these two forces, and that will be, yeah, they'll just be saying D is equal to W. But let's first see what W is. So this is our force balance equation, and W is simply m times g, or you can call it rho times volume times g. Yeah, let's keep all these things as it is for now. Okay, this is volume. So volume of a sphere is given by 4 by 3 pi d by 2 cube, and there is a g here. So this is rho 4 by 3 pi d cube by 8 times g. So this is W for us. Now, in order to calculate D, Yeah, let's just write the expression of D here first. So this is CD times zero point 0.5 rho V square pi D square by 4. Right, so first thing is to calculate CD, which is 24 over RE. And from the last slide, we already know that RE is nothing but rho times V times the diameter D and mu, which will come in the denominator now. So yeah, let's plug this in into this equation. Let's say this is equation 1. Let's plug everything into equation 1 and try to, since everything else is known to us, we only need to find V, and then that is what is asked in the question. So let's try to do that. So now first let's see D. So D is CD. CD is 24 times mu over rho times V times D into zero point 0.5. Zero point 0.5 we can write as 1 by 2 rho V square pi D square over 4, and this will be equal to the weight of the ball, which is just this one. So here we can write rho 4 by 3 pi D cube over 8 times G. So you can see from here this D square cancels the D cube, and there will be some other cancellation. So 4 times 2 is 8. That cancels this denominator 8. Pi and pi gets cancelled out. One row cancels out from here. Also 1v will cancel out from here. And this 4 you can divide both sides by 4. So this will cancel out and this 4 will give you 6 here. So in the end you will be left with velocity v is equal to, so this 6 goes in the denominator on the right hand side, 1 over 18, and there will be a g here from this, and there will be a rho and a d and a mu in the denominator. So let's now finally plug in all the values. So 1 over 18, g is, they are asked us to put g as 10, so this will be into 10. Rho we just saw was 11 into 10 is to the power 3. D is zero point 0.1 into 10 is to the power minus 3, and mu is 1.1 into 10 is to the power minus 3. So I guess if you solve this, yeah, so this 10 and this zero point 0.1 will cancel out. This 10 to the 3 and 10 to the minus 3 will cancel out.
Excuse me, sir.
Yeah, Ashwin. I
So
think
actually it must be d square, I think.
just a minute. Where is it?
Because we have a d in the denominator left side.
Yeah. Good spot. So yeah. So there are two d's here, so it will be d square actually. So okay, we can just say 0.1 into 10 to the power minus 3 again. Yeah, then in that case, this 11 and 1.1 will cancel out. It will give you a 10. This 10 is to the power minus 3 and 10 is to the power minus 3 will cancel out, and this 10 and 0.1 will cancel out. So in the end, you will just be left with 1 by 8. You can, if you don't follow this right now, you can do this calculation again. But yeah, in the end, you'll get 1 by 18, and that is option C. That's the correct option for this problem. So is this clear now, or if someone has any doubts, they can ask. Okay, I guess not. Let's move on to the next one then. Yeah, this is question from GATE 2021, set 1 ME. And the question is, a pressure measurement device fitted on the surface of a submarine located at a depth h below the surface of an ocean reads an absolute pressure of 4.2 megapascal. The density of seawater is 1050 kg per meter cube. The atmospheric pressure is 101 kilopascal, and the acceleration due to gravity is 9.8 meter per second square. And they are asking us to calculate the depth h in meters. So this question, I guess, simply just a matter of changing everything into SI units. That's all you need to do. And you need to know this hydrostatic pressure. So okay, if you have some fluid, so this is some fluid here. So the weight of this fluid will exert some pressure at some point, at every point in this vertical column, and that pressure only depends upon the height, nothing else. And that's called the hydrostatic pressure. So for this point A, this hydrostatic pressure will be given by the pressure at the top of the surface, which is the atmospheric pressure, plus rho times g times h, where rho is the density of this fluid, g is the acceleration due to gravity, and h is the height of the point h, height of the point A from the surface. So that's all you need to know in order to solve this question, just the hydrostatic pressure. And yeah, so it's just a matter of plugging in the formula. So please try this one, guys. I will wait for, I guess, 2-3 minutes, and write your answers in the chat. And please make sure you convert all the units properly. Otherwise, there's a chance of making a mistake. Yeah, I think, yeah, Priyanka has already solved it. Others also, please write their answers. So the formula is, I'll write down the formula here again. So this pressure will be pressure at atmosphere plus rho times g times some h. And I suppose they are asking us to calculate h. So h is what you need to find.
Done, sir.
What did you get, Abhijit?
Yes, sir.
Uh,
Yeah, 398.34.
okay, right. Yeah. So yeah, yeah. The correct answer is 398.
Sir, 397.94, sir.
397.94. Okay, maybe there is some approximation that you have done, but yeah, I think 398 is what you should get exactly.
Okay, sir.
Yeah. So while approximating, probably put all the values until the end. So just like how I did in the last question, or last
Sir,
question.
sir,
And
should we put G equal to 10, sir?
no, 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 no,
Instead of
no, no. See
9.8.
here in the question, they have straight away said that G is 9.8. So doesn't make sense to take G as 10. And if it is not mentioned, please don't take G as 10 unless they are mentioning it. So in the last question, if you see, yeah, here they had said okay, G could be taken as 10. I don't know if you see this. Yeah, here. Then okay, you can for the ease of calculation you can take G as 10. But here in this question, yeah, they have very specifically mentioned that G should be 9.8. And again, if nothing is given, take G as 9.8 or 9.81 if you want to be even more precise, but don't take it as 10.
Okay, sir.
Yeah. So everyone has solved this, or if someone has any doubts about this question, let me know. Otherwise, I'll move on to the next one because if everyone has solved this, then there is no point solving it again. Yeah, I think we will move on to the next one then. Okay, yeah, this is a recent question that came in this year's GATE exam. And here they have given us a tube of uniform diameter D, which is immersed in a steady flowing inviscid liquid stream. Please note these three assumptions: steady and inviscid liquid of velocity v as shown in the figure, and gravitational acceleration is given by g. The volume flow rate through the tube is, so they are asking us to calculate the volume flow rate. Volume flow rate is given just by the area times the velocity of the, the area through which the flow is happening, and the velocity with which the fluid is exiting that cross sectional area. That gives you the volume flow rate. Now these are the four options given to us, and so anyone has any ideas how to solve this? Come on, guys, you can. Take guesses also. No harm in trying, right?
So by applying Bernoulli's theorem.
Yeah, exactly. Yeah, yeah, you're on the right track, Abhijit.
Hello.
Yeah, someone was saying something. Abhijit was right. We have to apply the Bernoulli's theorem.
Sir,
Yeah.
if we get problem from orifice meter or venturi then Bernoulli's theorem or like that.
Uh, yeah, orifice and venturi, I think we will do eventually. That also, that is just hydrostatic pressure, right? You have to balance the hydrostatic pressures in
Yes.
orifice, venturi. Yeah,
The-
manometers, and then yeah, I think in venturi you have to apply the Bernoulli's. But yeah, you are right. So you need to apply the Bernoulli's equation here, and we had seen the Bernoulli's equation. So one good hint is always keep in mind these three assumptions, and wherever you see in the question that these three assumptions are being mentioned, then you should already get a hint that okay, I mean this might be a question where Bernoulli's equation can be applied to solve for the answer. So assumptions are steady flow, inviscid flow, and constant density flow. Inviscid means no viscosity. Steady flow means that you have the tendency of the local tendency or the local acceleration of flow being equal to zero, or constant velocity as in this question. So here they have given us liquid stream of velocity v, and constant density fluid means that the density does not change, or the flow is incompressible. So yeah, knowing all this, let's try to solve this question. So here you have some flow. First thing is let's try to calculate the okay, try to apply the Bernoulli's
Sir,
theorem.
option D, sir.
Yeah, you're right, Abhijit. Option D is correct. So we'll apply the Bernoulli's principle between 1 and 2. So 1 and 2. We'll apply the Bernoulli's principle. So P2 over rho g plus P2 square over 2g plus oh, yeah, Z2 is equal to, so from here I have taken this length to be Z2 is equal to,
Excuse me, sir.
yeah, Ashwin,
Sir, actually, this is like a river, no, sir?
this is like what?
A river.
I don't understand. What do you mean by river?
Open to atmosphere.
Yeah, on top, yes. Yeah, yeah, okay. Here also you can think of it as river. Yeah, any kind of flow, right? Could be in a swimming pool also. Who knows?
Yes.
Yeah, yeah. Could be in a large tank also. I don't know why did you specifically say river, but yeah, that also works. So this is P1 over rho g plus V1 square over 2g plus Z1. Right. Okay, so at the top you have some atmospheric pressure. So okay, this P2 is probably you can take that as 0, and then you'll have this yeah, so basically you can calculate P1 from here. So P1 over rho g will just be okay. Yeah, also the velocity in this flow will be same because okay, here the orifice is same, so V1 will be equal to V2. That also you have to keep in mind as the flow through the this tube is same, and it is of uniform diameter as T1 is equal to T2. Right. No, wait a minute.
So V2 will be 0, right? Because it comes to rest.
I think you are right. Yeah, yeah. Okay, yeah, yeah. Sorry, my bad. Yeah. So the whole point is this will have, even with same diameter, uh, this will have some different velocity because the flow rate will be different. So yeah, V2 will be equal to 0 because this comes to rest at top. And then I guess you can take this out. This goes to 0. And then P1 over rho g just becomes, okay, this also goes, just a minute. P1 over rho g becomes Z2 minus Z1. And if you look at Z2 minus Z1 carefully, this will be nothing but H1 plus H2. Because, okay, they have given it in terms of H1 plus H2, and that is just your, yeah, that is just your H1 plus H2 is Z2 minus Z1. So now we have P1 here, and this you could have also found if you knew about hydrostatic pressure. And since this only depends upon vertical, so the pressure here will be same as pressure here in the tube. And because this height is h1 plus h2, so you can just call it p rho g h1 plus h2. But anyway, once you have the pressure here, now we need to apply the Bernoulli's somewhere between this point and this point. So let's call this point as O, and this is already 1 for us. And first see what pressure at O is. So that is simply again the hydrostatic pressure, and here this is given as H1.
Sir, where is V1?
Z1 is this. So from the bottom, let's say this is your bottom.
No, sir, V1.
Oh, v1 is the velocity here at the just at the entrance of here.
So, but when you apply Bernoulli's equation 1 and 2, V2 is 0, but V1 is not 0, na?
At the entrance it won't be zero, right? Because inside the pipe something is going, some velocity.
Sir, at top of tube, they have shown arrow. It means fluid might be flowing.
Mm, you say the fluid might be flowing. I see. The tube of uniform diameter T is immersed in a steady flowing inviscid liquid stream. Gravitational acceleration is given by G. The volume flow rate through the tube is. Yeah, okay. Maybe so let's not apply Bernoulli here, even without applying Bernoulli, but you see that the pressure at P1 and P2 will be same, right? Not P2, I mean the pressure here and the pressure here. That simply comes from hydrostatic law, and that will eventually give you P1 to be equal to rho g times H1 plus H2, and then you can apply. Okay, first you need to calculate the pressure at P0, which will simply be rho c times H1, because that's the depth until which the fluid will experience the pressure at P naught. And then I guess you can apply the Bernoulli between 0 and 1. If you apply the Bernoulli's equation between 0 and 1, you can say that P naught over rho g plus V square over 2g. So here V naught is just V because they have given us this is some constant uh, velocity stream, plus Z1, which will be equal to, okay, Z naught, which will be equal to Z1, will be equal to P1 over rho g plus V1 square over 2g plus Z2. Now from here, not Z2, Z1, sorry. Now since 0 and 1 are the same height, Z1 and Z0 will cancel out. And yeah, so this then becomes, since P0 is rho g H1 and P1 is rho g H1 plus H2, so you can say that P1 square over 2g will just be equal to V square over 2g plus H1 minus H1 minus H2. So this H1 and H1 gets cancelled, so only H2 will remain. And from here you can calculate V1 square to be equal to V square minus 2g H2, and this will give you V1 to be equal to square root of V square minus 2g H2. And if you know this V1, then in order to calculate the flow rate, so this volume flow rate, so this volume flow rate will be equal to V1 times the area of the tube, And the area of the tube, since it's a cylindrical tube of diameter d, you can just say that this is p times d square over 4, and v1 is just v square minus 2gh2. So from here you can calculate this, and then I guess this option D is correct. And I suppose when we say that the velocity at 2 is 0, so maybe this comes just at the brim and it does not overflow. So that's how the velocity, maybe if you take 2 somewhere here, then this 2 will be equal to 0, right? So I guess the fluid will not flow from the top, and then you can apply Bernoulli between 1 and 2. But in any case, you can also use the hydrostatic law to get P1, and then from P1 you can calculate V1, and from V1 you can calculate the volume flow rate.
Sir, it may be tube is constant diameter, then velocity is same at 1 and 2.
Mm. Yeah, so if the flow is same, the velocity should be same between 1 and 2. But I guess that will apply when your tube is horizontal. So here, this is not a horizontal tube. So there might be some losses at these corners.
Yes, yes.
Uh, okay, then let's move on to the next question. This is also a recent question from GATE 2022. This is just some theoretical question. It says that the two-dimensional momentum equation for natural convection. Okay, I guess this is more related to heat transfer than fluid mechanics, but it's good to know this even in the fluid mechanics literature. So the momentum equation for natural convection over surface immersed in a quiescent fluid at temperature T infinity. That is the equation, and all these terms are the name of all these terms are given, and then they are asking the term g beta t minus t infinity represents. So yeah, anybody wants to tell me what this term represents out of these four options? See, I mean, I guess first option A and option B you can outrightly reject because this has some dimensions. So u du dx will have some dimension, right? It will be the dimension of acceleration, meter per second square. And this is a ratio of force by force. So this becomes dimensionless. So in any case, it can't be A and it can't be B. Among C and D, you have to decide which one this g beta t minus t infinity represents. So which one do you think is it?
D might be D, might be D, sir.
Why do you say that?
Uh, just guessing, sir.
Hmm.
Sir, probably because the other term is already viscous force per
Yeah,
unit
yeah,
mass.
perfect. Yeah, so okay. So we solve this just by eliminating all the other three terms. You can simply say that this is the term that they have given that mu is the kinematic viscosity. So of course this term will in a way represent the viscous force because mu is attached to it. Then this term is the only one left, and then okay, this is the buoyancy force per unit mass. So that's how you can solve this. But it's good to know that the ratio of inertia force to viscous force, we had just seen this, is the Reynolds number, and the ratio of buoyancy force to viscous force is the Grashof number. So this divided by okay, in some non-dimensional version of this will give you the Grashof number. This will give you the Reynolds number. and the viscous force per unit mass is this, and this is the buoyancy force per unit mass. So here, how does buoyancy come? So change in temperature will cause a change in density, and we already have seen that the buoyancy force comes because the difference in the density of the fluid and the body which we immerse in a fluid. So I think in one of the question we had this ball which was immersed in a liquid. Then it can experience some upwards for buoyancy force or downwards, depending upon the
There is a
density.
volume expansion as well, sir.
Sorry.
A volume expansion
Yeah,
would
volume
work here
expansion is
to
beta, right?
yes, sir.
This is some property of the fluid. So it will beta will be different for different fluids. But if you, let's say, heat something, it will expand, and then that coefficient of expansion is fixed, given by this beta.
Okay.
Yeah. So if so, I was just saying that if the ball had the same density as the liquid which it was immersed in, then it won't experience any buoyant force. So this density difference gives you the buoyancy force, and then this term represents it in terms of the temperature difference. Yeah. So this was some question from theory, and okay, this is from GATE 2018, and here in this question they have given us a tank which is open at the top with water level of 1 meter, and a hole at a height of h 0.5 meter is given. A free jet leaves horizontally from the smooth hole. The distance x where the jet strikes the floor is. Yeah, so again, anybody wants to take a crack at it? So what do you guys think will be the correct approach of solving this question?
So should we calculate the time at first?
Time of what?
Uh, height of the water. I mean, by using Torricelli formula,
So what is
root
this
of 2
formula?
V equal to root of 2gh.
And what is V here and what is H here?
Okay, let me.
We can get V from Torricelli's formula, and can we apply V square minus U square
Right. So what is the Torricelli's formula, Priyanka?
root 2g height from the here.
Can you repeat height
So
from height from?
point height,
Height from the surface of water, which is
ground, yeah.
exposed to atmosphere to the free jet.
Okay, yeah. Yeah, so from that you'll get some velocity, right?
Yes.
And from that velocity, you are saying you can apply u square.
Uh,
Sorry,
V square minus U square 2a. Can we do like that?
but a is not given to us.
We can take A as G.
Yeah, we can take a as g, but u is in x direction, g is in y direction. That velocity that which you calculate from Torricelli. So here I think in here also they say that the free jet leaves horizontally, right?
Yes.
So I suppose the velocity here will be ux, and uy is not uy is zero basically. So if you say u square minus v square, then you will need a velocity at this end, which you again don't know.
Velocity at the striking point will be vertically downward.
Yes, but what will be that velocity?
No, but
Can't we?
horizontal component at that point will be zero. So initially we have something, and at finally that component is 0.
Yeah, and then you're saying v square minus u square is equal to 2as. But that a is in a vertical, the acceleration is in the vertical direction.
No, from initial equation v is equal to u plus at, we will get time.
Ah, v is equal to u plus at, you are saying in x or in the y direction.
In x direction.
Right. So you know, yeah, v is 0, u is the torusol is velocity, acceleration is what then in the x direction. Okay. Anyway, I guess all of you are in the right direction. So first thing is to apply the Torres-Solis law. So here in this schematic, I have written down both these two formulas that you need. First one is to, if you are going to solve it through, I mean, step by step, first calculating velocity, then calculating, I guess, some time, and then from this time you calculate the distance x, r or r. Then you need to first calculate the horizontal velocity at the orifice, which is given by this v is equal to root 2 gh, where h, as Priyanka had said, that is the height of the fluid from the top surface till the orifice. Alright, so this gives you the velocity. But if you want to directly calculate and want to memorize this formula, that also works. So this gives you the range, or r, which is equal to 2 times this distance, the product of this distance and this distance. So okay, if this is h, small h, and the total height is capital H, then this becomes capital H minus small h. Right. So the range is nothing but, range being r, is nothing but 2 times the product of this height and this height to the square root. So let's just look at how this expression comes, so that okay, if even if you can't memorize it, you can always derive it. So we'll make some container, let's say, and this is filled up until here. This is your capital H, and somewhere here you have some orifice from which the fluid is squirting out, right? And this you can call as, okay, maybe this is our small h, then this naturally becomes capital H minus small h. So again, you can apply the Bernoulli's law first to calculate the, okay, first one thing you need to assume here is, before applying this Torres-Solis law, so this formula works with some assumption, apart from that, all the assumptions for Bernoulli's principle, which were steady flow, inviscid flow, and incompressible flow or constant density flow. Apart from that, you also need to assume that, let's say, this is some area A1 and this orifice has some area A2, cross-sectional area. You need to assume that A1 is much larger than A2. So if that is the case, then you can actually say that this, uh, so from that you can just say that V1 is much larger than V2, or you can just neglect your, sorry, so this will be, yeah, V2 is much larger than V1, and then you can neglect V2 or V1, in fact. So then if we apply this Bernoulli's principle, you can say that P over rho G plus V square over 2G plus Z1 here. So this is 1, and just at the brain this is 2, V2 over rho G plus V2 square over 2G plus C2. Right, so Z1 and Z2 are just, let's say, if this is the orifice I, from some datum this is Z2 and this will be Z1. So from here, I guess because both are at the atmospheric pressure, you can simply take this out. Sorry, and you can also take your V1 out, since the area here is much larger. Then the velocity with which the flow exits from the small orifice just becomes V2 square is equal to Z1 minus Z2 times 2G. And if you see, this Z1 minus Z2 will be nothing but your small h. So this is 2gh, and then the velocity V2 becomes root 2gh, and I think that's what we had here. Oh, sorry. Yeah. So that's what we had here. This is the velocity of exit from the orifice. Now, if you have this velocity, let's try to calculate the time period with which so the time it takes for this flow to hit the surface, and let's say this is r. So actually what you can do is you can apply this. So this is your from the laws of motion, you can just apply this y is equal to ut plus half gt square, and u here, since this is purely horizontal, so this is in y direction, or you can say vertical. So this we already see is capital H minus small h, capital S minus small h is equal to, since u is 0 here, this ut goes away, and you just have half gt square, and from here you can calculate the time period. So this will be equal to 2 times capital H minus small h over g to the under root 2. Yeah, I think this is correct. Now once you know the time period, it's pretty straightforward to calculate the acceleration now. So this r will simply be equal to, not the acceleration, just the distance in the x direction. This will be equal to the time times the velocity, which we had calculated here. So this time is 2 times capital H minus small h over g, and this is root 2 gh. And if you calculate, if you can cancel g out, so these 2 square root of 2 will come out of the square root, and this will simply be capital H minus small h times small h. So this is, I think we have done this in projectile motions in our physics classes in +1 and +2. How to calculate the range of the projectile and all of those things. It's very similar to that. But if you don't want to go through all this derivation, you can just memorize these two formulas. One is for the exit velocity at the orifice, and the other one is for the distance in x direction with, which the flow will travel before hitting the surface. And that only depends upon the height, the total height of the flow, and total height of the fluid, and the height where the orifice is located. That's all. So it's a small h and this capital H. Okay, now I guess we have spent fair bit of time just deriving this formula. So this makes our job easier here when we are solving this. So capital H here is 1 meter, Small h here is 0.5 meters. And they are asking us to calculate this capital X, which was R for us in the derivation. And we have just seen that this will be equal to 2 times capital H times capital H minus small h. So this is 2 times 1 and yeah, so this will be, oh sorry, so this is not capital H, this I wrote it wrong. So this is small h times capital H minus small h. So yeah, this will be 0.5 and this is 1 minus 0.5, again 0.5. So the 0.5 comes out of the square root and then you get that is 1 meter. That is your x. So that's option B. So as I said, you can either memorize the formula or you can okay, do it from first principles also, whatever works. But one assumption you need to remember is, apart from the Bernoulli's assumptions for Bernoulli's principle, you need to have the dia of this thing being much larger than the orifice or the small hole that they are mentioning. Yeah, anyone has any doubts on this?
No, sir.
Okay, so I guess that's it for today. Yeah, so this is again for next time you guys can try this. I think last time someone had asked me to solve this one in the class. Somehow I did not get the time. Maybe if any one of you can solve this, we will discuss this first thing in the next class. Or yeah, you can just tell me the answer to this in the next class. So I'll put this in the slide again, and you guys can try this.
Sir,
Yeah.
sir, could you please show me the first 2 or 3 slides because I joined late.
Yeah, I'll share the slides, Vijit, so you can yeah, you can take a look at the
Okay,
slides
okay, sir. Pardon me.
later.
Actually,
Yeah.
okay.
Excuse me, sir.
Yeah, Ashwin, tell me.
So can you kindly tell the concept behind this homework question so that we can try it?
Yeah, so I'll give
Just
you a
in brief.
hint. I'll give you a hint. So this is more of a mechanics problem than a engineering mechanics problem than a fluid mechanics problem. But so they are asking you to. So there is this sprinkler here, and the flow is equally going in these two directions. They are asking you to
Same time,
calculate the
momentum and
angular
torque.
velocity of the sprinkler. And the hint for this question is you have to balance the torque at this hinge point. Right, you just need to know that, that's all. And then I guess you need to like know how to calculate the moments and how to calculate the torque at this point. And if you know that, then just calculate, matter of calculations, that's all. But I guess that's enough hint. You can try it and let me
Yes,
know,
sir, sure.
yeah, if you were able to solve it. Someone is just a minute. Yeah. Yeah. Ashwin, you were saying something.
Sir, actually, one small request.
Yeah. Tell me.
If time permits, will we be able to cover fluid machines as well?
Fluid. Yeah, I think I
After
told you
fluid
fluid
machines.
machine is difficult for me to cover because I am completely out of touch with that subject. So if someone else is taking it, that would be good. I cannot say that I will be taking fluid machinery. I think you're talking about those Pelton turbine and all of those things, right?
Yes, sir. Yes.
Yeah, that would be out of my hand section. I mean, I can't. I'll have to do a lot of background study for this, so I can't say that I will be taking that.
Okay, sir.
Yeah.
Sir,
Yeah, Suraj.
I want tips regarding how much long previous year questions needed to be done for gate?
How okay? How much? How many have you done? Have you started doing previous year questions?
Yes, sir.
So I think okay, if everyone is here, I will just tell everyone that at least from 2011 to 2021, because I think there was some change in format at around 2011. You have to solve every question from 2011 to 2021 or 22 now, and that will be fine. But okay, more practice never hurts. So I would say solve all the questions even before 2011, but there is no way you can neglect questions from 2011 till 2022. Those you have to solve every question.
Okay,
Yeah, every question multiple times. Yeah.
every question multiple
Yeah,
times.
yeah, because one time you solve, maybe some questions are easy, you can do it in one go, but there are some tricky questions that require you to like revisit those concepts again and again, so that if something similar comes in the exam, you don't do any mistakes. So yeah,
And with these questions, how much score we can get?
if you just do previous year questions,
Ah, yes.
if you do previous year questions multiple times, I'm pretty sure you'll get something. Okay, yeah, it's hard to say, but for 60 plus, you can easily get just by solving previous year questions, just by solving them. Because I don't know, you guys have seen previous year exams, right? The pattern is similar exactly. Now, if this year someone wants to like play with students and then they give completely different format, then it's a different story. But year by year, the values change. The format based on which the question come never changes. So just by doing previous year question, you can at least get 60 to 70 marks easily.
Okay, sir.
Yeah, yeah.
So for all the classes that you've taken so far, where can I find the slides?
Yeah, okay, yeah. I think you were the one who wrote that in chat also, right? Yeah, so there is this Google Drive where I have put all the recordings as well as the lecture slides. Uh, can someone put it in the chat, or okay, maybe I'll try to put, yeah, yeah, Priyanka, I think last time also she put it. So I think she has put it. You can check this out. Uh, if yeah, I think it will work for everyone now, because I had granted access to everyone who has the link. And here you will find folders with lecture videos as well as the lecture slides from last 11. So we did some 12 sessions before some break, 2 3 week break, and then we have started again with this phase 2, and this is the second week of phase 2.